Good morning, pre-calculus students. Can everybody hear me? Is my voice coming across clearly?
Yes,
Kaylin?
sir.
Excellent, thank you. Sometimes the technology glitches and I don't want to be speaking to my home and not to you. So thank you for confirming that. Okay, so what we did last class is have a little excursion back to the word problems from college algebra, and I taught you some techniques concerning symbolic computation, where we break down numbers like we do algebraic objects and solve problems in a way that makes it at least more efficient and more algebraically pleasing. And then, of course, we reviewed a little bit about some inequalities. So what I want to do today is do some more inequalities, say a little bit more about the absolute value, and then move into the realm of the function. Now, we've actually been talking about functions, in the class. We use the function notation, but we want to go back and hit some of the main concepts of the function. So right now, what I want to do is go ahead and share the screen, and let's discuss a word problem with the inequality computation. Now, like I always do, and I tell all of my students, I work problems that you find in your WebAssign, and often what will happen during my office hours or conference hours, or if one of you actually sends me a question with the WebAssign messaging that turns out to be a really good problem, I'll sometimes include that in the lecture just because I think, well, that might be something everybody wants to see. So this is a problem similar to that. There are a couple of these that I want to go through. Now, this of course is function notation, but right now it's just going to be a symbol to represent this formula. So this formula here, 516 plus 16t minus 16t squared, describes the height of a ball above the ground. So when you all take your physics classes, you will do the particle kinematics that will allow you to prove this equation, and it will involve derivatives and integrals, which by that time you'll be very good at doing. Now, here's what the question is. When is the ball at least 36 feet above the ground? Now, when we look at a question like this is really a good practice, because just like doing the word problems, we want to be able to, let me adjust this just a little bit and move this, there we go. We want to be able to make sure that we describe the mathematics as the words have directed us to do. So now basically we take this equation and we want it to be at least 36, so greater than or equal to 36. So equivalently, when we solve this, we have, and I'll go ahead and write this in descending order, negative 16t squared plus 16t plus 516 is at least greater than or equal to 36. At least and at most are phrases that you use in science. You use them in probability. For instance, you might say, what is the probability that the chance of rain is at least 10%? Things like that. These are common phrases that you hear in everyday language. You would think we'd be better at interpreting them. So now when we look at this, we think about what we've been doing all along. We have extra stuff. So the first thing I'm going to do, I'm going to break this down into two pieces like we were doing the word problems last time. We've got a 4 in all of these terms. So let's first divide by 4. So we're going to have a negative 4t squared plus a 4t plus, now divide, we've got what, a 1. Then we have an 11, so that's going to be what? That's going to be 2. And then we have a 36, so that'll be a 9, 129. It's always nice when the numbers aren't so large. Greater than or equal to, divided by 4, we have a 9. Now, when you look at this particular example, at least the numbers are in good shape. And then we're thinking about maybe moving the 9 over so we can get our 0. But I wanted to do this in 2 steps. So now let's go ahead and make the leading coefficient positive. So let me just write down what we've done here. Divide by 4. Notice 4 is a positive number, so this inequality stayed the same. Now, just because we like to have the leading coefficient positive just for arithmetic reasons, we want to now multiply by -1. Now, again, this is a negative, this is a number less than 0, so we will have to reverse this. So let's go ahead and just flip all of the signs. So 4t squared minus 4t minus 129 is less than or equal to -9. Now again, you don't have to break all of this down into these many steps, but I would suggest it for now until you build your confidence. It is so easy to think, well, I'm just going to reduce this, and you hit the equation with a negative number and you forget this. It's really easy to forget because again, it's a theorem. It's a little less apparent. It's more abstract. And now what we want to do is take the -9 over. So we're going to add 9 to everything. So add 9 to both sides of the equation. So we're looking for a standard form. So of course, when we add 9 to -129, we get a -120. Now I wanted to start with this problem because the numbers are a little bit more user-friendly. Lots of you will send me messages and say, I think I've got the idea, I'm following what you did in lecture, but something didn't work out quite right. And usually it just might be something like forgetting to switch the inequality or trying to work with the AC method and it didn't quite go through. Now, what I want to do is take this one more step. You're thinking, well, look at it now. We have 4s and everything again. So smaller numbers are easier. So divide by 4. The idea is as we move through the problem, we subtract and add, we can introduce more common factors. So again, let's divide by 4. T squared minus t, and then of course we get the -30 here. Now, what I do and what I found is that if you look at this equation, put all of the terms on one side, and then you try to factor it. This is basically what I've been teaching you from day one. We want to get rid of baggage, so to speak. We want to get rid of numbers that have no bearing on the solution. So now look at this. We started with something that's usually unfortunate, and now we have something that is simple. We can factor this in our sleep. The idea is now we have a very simple Professor Ron's AC lemma. So notice here we have a 1 and a -30. So we have AC, again, very simple to factor. So we have 1 times the -30. Now we know that we want the sum, the z and the w, to be -1. So we don't really need the 1, but we know we can write the -30 as a -6 times a 5. So don't assume anything about these problems. Don't just say, well, I think this is the factoring. This looks pretty easy. Go ahead and work it out, even if it's simple. We don't really need to factor this by grouping because it's so easy here. But now we can say that will work. So we have t minus a 6 times t plus a 5 less than or equal to 0. Now, again, let me just impress upon you that you continue to do these types of computations in calculus, especially Cal 1, all of them, Cal 1, Cal 2, and Cal 3. I'm teaching a Calculus 2 class now, and again, just to make you understand, these techniques are extremely important. You'll use them over and over again. Now, notice we're at the standard form. We just want to look for our boundary values. We see that we get a 6 and a negative 5. What makes this 0? Clearly 6. What makes this 0? Negative 5. So we say boundary values. 6, negative 5. Now, this is an easy one because the leading coefficient here is a positive. So we can draw our number line, or you can just say, I know this, but that's okay. We always want to verify things. Now, like I said before, we can do the sign test, but notice since the leading coefficient is positive, we know that as t gets big, the graph will be above the x-axis. And then, of course, as t becomes negatively infinite, the negative times the negative is positive. So we're thinking above, below, above. So again, that's appealing to the fact that both of these zeros have multiplicity 1. But again, like I told you before, you can have the t minus 6, t plus 5. And we could just take a test point. So we could do like a negative 10. These are not unique. You can pick any point you like. I just pick easy ones, 0, and then a positive 10. So now when we substitute the negative 10, this factor is clearly negative. And the negative 10 here, it's clearly negative. So it does verify that this is above, that is positive. So that's no good. We could have gone ahead and put the x there now because we want less than or equal to 0. Of course, this makes the equation 0, and this makes the equation 0, so they get checks. Now here, of course, we think we're going to get a check. So if we substitute 0, again, this factor is negative, but this factor is positive. Negative times a positive, negative. So that's good. We expected that. And then, of course, here we're going to get positive again if we substitute 10 into the first factor plus, and if we substitute 10 into the second factor plus. So we want to make the factors simplified enough so that we can easily determine what the sign is. It does not matter what the actual number is, so don't spend time computing that. That's a waste of time. So now we've got a plus, and so that's no good. So when we look at this, we see that this equation is satisfied if and only if, and sometimes I leave these out, we can put those for all of these, if and only if this is satisfied, if and only if x lives in this region. So we say, let me move this up a little bit. We now say that the values in this case, well, actually these are t's, the value of t in this case would be from -5 to 6 inclusive. So remember, when you're doing your WebAssign, if you have the equal to with the inequality, you need to use the brackets. And so we have a 6 and a bracket. And there we have it. Now, one thing we need to look at here to amplify this, which I will finish, here, and I need to note this, t represents time. So this means that t is non-negative. So we must restrict to the final interval of 0 to 6. So this is true for this inequality, but for the word problem, so we're going to say word problem, time is non-negative. I have lots of students and they send me this problem and they say, well, I know I worked this correctly. And I said, you did. I said, excellent. But just remember, we have to think that we've got a real world problem where time is non-negative. So when we complete the problem, we move to this. And then this would be what we would type into WebAssign. Okay? So again, this, if I had just given you this inequality here, you'd say, that's easy, Professor Ron, I can do that. But the key is just like doing the word problems last lecture, we have to take all of the words and make equations out of them and then amplify the problem by doing symbolic logic, creating a situation that's easy, difficult, easy. And then at the very bottom, everybody, interpretation. So what I like to do, for instance, when I test, when I give you tests, you know, I like to be able to see what you've done. And so if you worked out a problem and you showed me all of this, then I would be convinced that you have a good understanding of the inequality process. So don't beat yourself up if WebAssign is like not agreeing with you. Just go back and read the problem and make sure there's not one aspect you forget. We all look for the answer and we all miss things, and that's just part of doing mathematics. Now let's look at another one. I think if we spend our time with some of these word problems, we actually get a lot better. Now, there was one additional problem that I wanted to share with you. There's a gas mileage problem, and it's like the last one. So this was another question that a student sent me. This was actually yesterday. And just like this problem, it presented some difficulties with the arithmetic that we had to adjust. That is, we had to make some arithmetic adjustments using symbolic computation to make it look simple or make it look easier to analyze. So I want to talk about this. Then I want to say a little bit about absolute value. Now, for those of you, some of you may end up being financiers. Maybe you will go into business, get an MBA. You have to know some calculus to do that. And so you may talk about revenue and cost. And then, of course, profit. There's a lot of good work in finance. So those of you that want to parlay your interest in math into finance, business, accounting, wonderful careers. And the more math you know, the better you're going to be. And you'll have a very rewarding life, just as if you were in the STEM. And I guess most of you probably STEM. Now, in this case, the problem gives a revenue, and we'll just use our function notation for now. This will just be a symbol, R for revenue. X is actually going to be number of units. So I'll write this over here. So we're producing units. So number of units. Now, what we're going to do, here's what the problem says. The revenue is 23X. That is, X is the number of units, and 23 times that will give you the money that you make in dollars, okay? And then the cost, which will represent with the C of X as a formula, will be 2,200. Again, that's a fixed cost, plus 10X. And then they give you this really unfortunate decimal, which you know Professor Ron's going to convert. I mean, we can't convert, ladies and gentlemen, the non-repeating decimals. Clearly, those are irrational. So pi and e, we're stuck with those. That's why we give them symbols. We have 0.0025 x squared. So For this particular process of producing X units, the revenue is 23X. The cost is $2,200 plus 10X plus 25 over 10,000 times X squared. And then, for instance, and this is what we want to do, the problem basically says this: determine the number of units to determine the X basically for a profit of at least, now I like the at least, of at least $5,675. Now, when you look at a problem like this, you're like, man, are these good numbers? Are these horrible numbers or whatever? Just remember that when you're doing the word problems, usually the numbers will be on your side. And of course, if I test you on something, there's an occasional time when you may need to use a quadratic formula. But in this particular problem, they're actually looking for you to factor. So now, what does this mean? First, we have to write the following: profit equals revenue minus cost. Maybe you've had a little business when you were growing up. Maybe you did a newspaper route, or maybe you sold lemonade on the street corner or whatever. You're very familiar with how much money you make, and then of course that's dependent on how expensive it is to run your business. And so now we can go ahead and write all this in. So revenue, so equivalently, we have 23X, and then we have to subtract all of these terms. So all of these are going to get a negative. So we subtract the cost, negative, negative, negative. So distribute. So I can't impress upon you how important it is to distribute. You can't just place a negative on the first term of the expression. It must cover all of them. And don't be upset about this. I have calculus students that do this. We all do it because we just get careless. So now when we have the negative, minus 2,200, minus 10x. And then minus, now I'm going to go ahead and write this as 25 over 10,000. That's what that decimal is. We've got 4 decimal places. And we have an x squared. And we want this to be at least $5,675. Trust me, when we factor these numbers, they are not unfortunate. They are actually good numbers. Now, what I want to do, and I'm going to do this in 2 steps again, just to make it easy. I want to write everything in descending order, collect some terms, and then we're going to run through with the negative to have the leading coefficient positive, because that makes the factoring process easier. Now, first, everybody notice this: 25 divides 100 4 times. So this is really a 1 over 400 with a negative sign. So let's go ahead and reduce that. Negative 1 over 400. I told you the numbers aren't too bad. They're not wonderful, but we'll survive. And then, of course, if we add the 2 terms with x, we'll get a plus 13. And then, of course, we have a minus 2,200. So we're just cleaning this up. We're not doing anything elaborate. Greater than or equal to 5, 6, 7, 5. Now, if you like, we can, and I'll do this in 2 steps. Let's just go ahead and run this guy over. I don't want you to do things 2 and 3 things at a time and then make a careless mistake. Let's just go ahead and break it down so we can see what we're doing. And so now we have minus 2,200 minus 5, 6, 7, 5. greater than or equal to 0. Now I'll just go over here, use this. Well, I don't want to use that space over here. I'm going to use that to do some factoring. So let's go ahead and add these numbers. Now I'm adding extra steps so you can be very careful. You can clearly leave out steps and consolidate. Now what we see, we have a 5 and a 7, and then we have an 8, and then we have a 7. Oh, sorry. Don't interchange things. We have a 5 and a 7, but in a different order. That would be rather unfortunate, because the way I've set this up and the way this problem is constructed is that this is a nice number. We can divide it by 25 and other things. So right now everything looks good. What I would recommend at this point is to think, let's look at what we did on the last problem. We pretty much want something like this if we can get it with a leading coefficient of 1. So this is where what I want to do is write down here, multiply, we'll do a twofer by -400. Now that I've broken this down enough, we're okay to get this out of the way. Now, when I do that, I'm going to have to switch this inequality, but the -400 here absorbs this. So I get x squared, and then I get a minus 13 times the 400 using the symbolic computation. This is so effective. Then notice we have a minus, so plus 400 times 7875. Now this is negative, so this must reverse, less than or equal to 0. Now, everything's fine. We're good to go. Look, we have a nice quadratic. Now, here's what I want to do before we finish the problem. If you look here, this is the kind of the highlighted number, so to speak. 4 times the 12, or excuse me, the 3 will be a 12, so that'll give us a 5200 negative. So equivalently, we have x squared minus 5200, like a deck of cards, plus 400 times 7875, less than or equal to 0. Now, this is what makes this particular problem doable. That is, now, again, this problem is given to you as a word problem, and again, it's set up, or if I had written it, it's set up so that x actually is integral. That is, you're going to get an interval that has integer endpoints. So what we want to do is just notice whatever numbers we get over here, the z and the w, they must have 2 zeros at the end. So that's going to help us factor. So here's what I want to do. Let's move our work right over here to the side so we do some factor trees. So this is why I did what I did yesterday, and I'm grateful to the student that asked about this question. I think it's an excellent problem. I was considering it, but after I helped him with the problem, I said, yeah, this is a good one. Now, let's start with the 7875. We're going to do the easiest part first, which is to divide by 25. We know it's divisible by 25 because 75 is divisible by 25. So 25 into 78 will go 3 times. Then that will leave us with a 37, so that's 1 time. And then the difference there is 12. 125 divisible by 25, yes, 5 times. So that's easy arithmetic there. And now that looks good. We're going to kind of hold on to that. Now here, if you like, we can divide by 5 again. So 5 into 31, that'll go 6 times. And then we have a 15, that'll go 3 times. Looking good. Oh, okay, well, now note. 9 times 7. Now, before I move any further, I'm thinking, I've got to have some zeros here. You know, I need some zeros. So let's just say here, 400. I know I can get 2 zeros if I have a 4 times 25. So that's a good deal. So here, I'm just going to say 4 times 100. Now, when I was actually looking at this, I thought to myself, okay, I need a Z and a W that sum to 5,200. I'm going to have 2 negatives, obviously, but that's no problem. Negative times a negative is positive. So now we can look here and say, okay, 7, this is where I started. 7 times 100 is 700. And then that's going to tell me that I need 4,500. If I add to 700, I get 5,200. So that's a clue. By looking at this and looking at the numbers I have here, I'm in good shape. Now, I'm going to use the other color here. This will give me a 100. And then the 5 times the 9 will give me the 45. So now what do I get? I get 4,500 and I get 700. And the sum is 5,200. That's how you do Professor Ron's lemma. And even when the numbers are unfortunate, you can still do it. This is a whole lot better than trying to do trial and error and you go crazy. So again, the idea here is that even though the problem itself is complicated, you learn it, you master it, and then if you see it later, you know how to do it. That's why you take classes, so you can take your learning to the next level. You learn techniques, you learn complicated problems, and then the next time you see a problem similar to that, you're ready to go. Now, this is just like the last problem. We don't need any fancy factoring by grouping. We got a leading coefficient, and we have our Z and our W if we just put 2 negatives with them to give us the negative 5,200. So this is a fun problem. Well, you know, we're enjoying ourselves. So we get minus 700 and X minus 4,500. So when you do your WebAssign will probably generate different numbers, but you'll have a little model to work with. Now, this is like the last problem. We know where the answer is going to be. So our boundary values, BVs, will be 700. What makes this factor 0? 700. What makes this factor 0? 4,500. So we can do the same thing we did before, and we won't have to take as long because we've been doing this many times. It's kind of getting repetitive. So again, if we think about just the fact that we have a quadratic with leading coefficient that's positive, as X gets really big, the graph is always above the X-axis, so it's going to be positive. And same for negative infinity. But at the zeros, because we have what? Multiplicity 1, the sign will change in here, just like we had before. So if we did our test points, we would verify this. I want you to be able to do this because really, ladies and gentlemen, it's easy when you've got a simple polynomial and you know that with a multiplicity 1 of a 0, the graph will have to cross at that 0. The sign will have to change. And so now notice, equal to 0, check. Equal to 0, check. Less than 0, check. These over here, no good because it's positive. But now notice, we don't have to worry like we did on the last problem where we had negative values for t. These are all positive. So this implies that the number of units that we need, let me right up here, will have to live between what two numbers? 700 and 4,500. So we say X lives between 700, 4,500. And why are we using the brackets? Well, you know that we have the equal to. So this problem is kind of like the word problems we've been doing. It showcases all of the techniques that are important to doing calculus. We have a description of a problem. We write the problem mathematically. And then we spend a lot of time making it simple. This is truly unfortunate. But if we can reduce it to something simple, then we have a chance of using the AC lemma, Professor Ron's AC lemma. And so what we see here is that this inequality problem showcases all of the important techniques that we need to remember. And I'll say this, why do I keep focusing on these types of techniques? Because when you do calculus, you are doing exactly this. You are doing this kind of manipulation where you have to be comfortable with the process. So what I will again emphasize, break everything down, take the steps slowly at first. Make sure as you work through, if you hit something with a negative like we did here, we reverse the sign. We reverse the direction of the inequality and then work it down. So you can see that why do we call this course pre-calculus? Well, it's preparation for the calculus. So you don't get the calculus and everything's automatically easy. You use everything that you've learned in this course. And what makes it hard is that you don't know when you're going to need to use this. It'll just get plopped in your lap. So this is a good example, and this should help you to do your WebAssign problems and hopefully give you a clue as to how you can do any problem that would have this inequality type word problem nature to it. Okay, excellent. Now, I want to say just a little bit. I had a couple of questions from some students with the absolute value before we start talking about functions, proper functions, you know, give a definition and then do a little bit about that. I think you'll find the work with functions to be pretty simple, ladies and gentlemen, because you got so much of that, at least in college algebra. So I had a student ask me about writing an interval that was connected with absolute value. So let me just remind you, we had the theorem about the conjunction. That is, we had C was positive, we had the conjunction and the disjunction. So if we had the absolute value of X is less than C, what did that mean? Well, that meant that we got a compound inequality, that X is between the additive inverse of C and C. Okay? That's what we call the conjunction. These are fairly archaic terms. I don't know why they fell out of fashion, but give it a name. That way you'll remember it. And then, of course, this one gets all the play in calculus. It is extremely important. Now, the other one that the student inquired about was the disjunction. Again, when you think about this intuitively, if C were equal to 5, then you would know that X would have to be bigger than 5, but also X could be less than -5 because all those absolute values would be bigger than 5, so to speak. So you get a situation where you get disjointed intervals as opposed to connected. So you get X greater than C or X less than the additive inverse of C. I know you know this, but I'm just reviewing it so you can tie into this as I look at this example. So the student asked about this, and so I'm going to give you a little, what do we say, recipe to do this. So here's an example. I'll say write the interval. I just made this up. You have these in your WebAssign. -3 to 7 as a symmetric interval using absolute value. Get this mouse out of the way. Using, oh, sorry. I think we need, for our English professors, we need an N. Using absolute value. Now, for instance, here's an easy one. Let me just do like, here's a little aside here. What if you had something that was clearly symmetric to 0? Say you had -5 to 5, like that. That's easy. There's the C right there. The C is 5. So you can say that is that. So to go backwards, you just say absolute value of X is less than 5. So that's the shorthand way of writing that. So if you have the interval from -5 to 5, you really have a symmetric interval about 0. So you have the 0 here, you have the -5, and you have the 5. And so you have what we call the symmetric interval about 0. And you see that 0 is the midpoint. So we say midpoint. So when you have something like this, it's not very difficult. You can, okay, there's my C. That's really what this is. And now using the absolute value, I have an interval about C that's symmetric, interval about 0 that's symmetric. That is, the distance from 0 to 5 is equal to the distance from 0 to -5. That's what we mean by symmetric. And I didn't say a whole lot about this at the time. And so when the student was asking about the WebAssign, I thought, yeah, this will be a good way to do a small introduction to what you'll do in calculus. Now, let's look at this one. This one's not written like this. So in order, here's the recipe. In order to do this, we first want to find the midpoint of this interval. So remember, if you have, here's the recipe for midpoint. If you have an interval on the real line, the midpoint, we'll just say MP, will just be the average of the left endpoint and the right endpoint. So you add them and divide by 2. That's the midpoint. That's what you learned probably in geometry or algebra 1. So this is the midpoint formula. I always say something about this in pre-cal, but everyone seems to forget it when they get to calculus. Maybe this time you all will remember it. Now I can do this. So for this interval, -3, and I chose nice numbers here. We'll say midpoint will be -3 plus 7. Remember, you just add them. Whatever they are, you add them. Don't do anything otherwise. Divide by 2. Well, that'll just be a 4 over 2, which is 2. So that's the midpoint. So now when we think about this, now when we look here, we see the distance from 2 to 7 is 5, and the distance from 2 to -3 is 5. So this is symmetric about 2, okay? So you're thinking, so how does this get me where I want to go? Well, now we're finished. The second part is just to write this way, and then we'll put in the 2. We have -3 is, I just came up with this little algorithm to make it a little bit easier. I mean, sometimes you can say, oh, well, you know, I just subtract 2 from everything, and that's right. But now we'll say symmetric about 2. So now to get that, we just subtract 2 from everything. So we get -3 minus 2, x minus 2, 7 minus 2. That's going to give us the C. Now, -3 minus 2 is -5. And 7 minus 2 is 5. So now this looks like this here. I mean, we're thinking now we have the C here. The C is 5. But we had to use the midpoint to translate everything because we didn't start out with symmetric. I mean, here, anything that looks like this will be symmetric about 0. There's no work to be done. You go automatically to this because there's your C right there. Now, the idea here is we had to do a little bit of an adjustment. So now when we look at this, we see the C is 5, and we just get absolute value of x minus 2 is less than 5. Now, in calculus, what happens is you do computations and you end up with an equation like this, but you may not have the same number. So you pick the smaller one to create the symmetric inequality so that this is still true. That's what you do in calculus. You do all of this work, and then you have the C from the limit problem, and then you move from here to the absolute value. Now, I know that this might be a little bit new to you, so you're going to have to think about this, but just remember, do the midpoint and then do the computation of subtracting the 2 throughout. That is, whatever you get here for the midpoint, this is what we subtract everywhere, midpoint. So subtract midpoint. Now, of course, if the signs change, things change. That's fine. That's okay. Just look at this as a way to actually do this problem without having to guess. That is, this will at least clue you into the fact that you can go to the number line and put in a 2 and go 5 units this way and 5 units that way, and then that gives you precisely this. So this is new. You may have talked about this maybe in college algebra. I'm not sure. I don't think there's as much attention given to the absolute value in college algebra, and we pretty much do it in pre-cal. So this is just a little introduction to how you can use this theorem. I mean, clearly I want you to be able to use this theorem to solve these inequalities, but there might just be a case where you have to go backwards. So now we're kind of looking to create this. So once we create that side, which we have here, we can go backwards. We can go to this. So this is basically the reverse problem. And again, try this when you're working with your WebAssign. The disjoints here, the disjunctions are very easy, but the process for the conjunction is a little bit more complicated, but it's certainly very doable. So I just wanted to say something about that so you feel a little bit more comfortable, okay? So when it comes to working with the elements of calculus, we're kind of stuck with absolute value. We're stuck with inequalities, equalities, symbolic computation. They are all part of the process. Now, one thing that I want to talk about now has to do with a topic that you spent quite a bit of time on in college algebra. Now, when it comes to working with functions, I think you're pretty good with the notation. What we want to do is just review some basic concepts. So next lecture, we can move on into the function transformations, you know, horizontal shifts, horizontal compression, stretching, things like that, vertical shifts, reflection and axes. Those are topics that are very important and that will get some use in your calculus courses. Again, you just don't know in calculus when you're going to have to use some trig. You're going to have to use Professor Ron's AC lemma. You're going to have to solve an inequality. I mean, these techniques you will become a master at doing. And so if you get to the university and you need a little extra money, you can tutor and teach other students about math that may not be STEM majors, that need a couple of math credits for their degree. So now what we want to do is talk about 2.1, which will be functions. And like I said before, the next topic after this will be the transformations. So basically, we want to talk about functions. Now, the definition of a function is very simple. We're going to move to the notation that we're most accustomed to. But first, I just want us to remind ourselves of what it means to define a function. We'll say a function, and we'll just call it f just for now. You can use any letter you like for a function to maybe give some idea as to what you think it might represent, like we use R for revenue and C for cost. A function f is a set, at least in the plane, is a set of ordered pairs. And often when we think of functions, at least in a math class, we would think that the ordered pairs would be those of numbers. And in pre-calculus, we focus on real numbers, such that. And here's the little rule for the functions. That is, we'll have an ordered pair AB, where we think of A as the first coordinate, and we think of B as the second coordinate. Sometimes we'll say input, output. We'll talk about those. So if we say that this ordered pair is an element of F, so you're thinking if a function is a set of ordered pairs, you can graph them in the plane, which we do without thinking about it. And if we say that AC is an element of F. Now, what I'm noting here is that we have two elements of the function, the elements being the ordered pairs, where the first coordinate in each of these elements is the same. That is A. All right. Well, if this is a function, then it must be the case that B equals C. And what this is saying is basically what you did in Algebra 1 and college algebra. Every first coordinate is paired with a unique second coordinate. So this just means every first coordinate, is paired with a unique second coordinate. Now, we could have functions where all the second coordinates are the same. That's fine. It's just a constant function. It just means, though, that we cannot have a situation where this is true and B does not equal C. That doesn't make sense for the definition of function. And I think something you learned in college algebra is that if you have the graph of a function, it must pass this. And that's basically the vertical line test. So this definition is really the vertical line test. But that's neither here nor there. I mean, vertical line test is fine, but the important part is understanding this. So now what I want to do is just say the first coordinate is often called the input, and the second coordinate is often called the output. So basically, we think of a function as a machine. Now, we don't normally spend a lot of time with finite numbers of elements in a function. Usually we have real value functions of a real variable, but just in the terminology, we will say the set of inputs for f, that is all the first coordinates, is called the domain. Just want to make sure that the terminology is good for everybody. I know this is kind of dry and boring, but we want to be on the same page. The set of outputs for f is called the range. Now, sometimes we don't really have a abbreviation for range, but a lot of times we'll say DOM for short for domain. We'll say domain of f, something like that. But if you're working with a function and you say domain, it's clear that's what you're talking about. But sometimes DOM of f is just shorthand for the domain of f. And again, if you use that or you don't, it is of no consequence. You just may see it written that way. So for instance, here's a simple example, and then we'll get back into our function notation. So say you have a function that's given in terms of ordered pairs. So say we have 1, 2. So the input would be 1, the output would be 2. We have, say, -3, 5. And maybe we have the square root of 2, 0. And then maybe we have 6, 2. Now, when we look at this, and I said it was a function, so I made sure that I gave you a function. Notice all of the first coordinates are paired with a unique second coordinate. We don't have a 1, 2, and then a 1, 2, or a 1, 0. That is, all of the first coordinates only occur once, so that we abide by this. Now, when you look here, we see that 1 has an output 2 and 6 has an output 2, which is fine. No problem with that. We just now know that this function is not 1-to-1, and we'll say more about that later. But now we can say domain. We'll just go ahead and write it out. The domain, again, is a set, which is all first coordinates, 1, -3, square root 2, and a 6. And the range will just be the set of outputs. We'll have a 2, we have a 5, we have a 0, and of course we already have 2 listed, so we don't have to write that again. So the idea about the function, you're thinking, well, this is kind of simple, but I think you know, at least from your previous experience, that this abstraction called the function is probably one of the most important concepts or objects in mathematics. The function is how we describe what we're doing. The inequalities that we solve were described using functions. When we talk about calculus, we talk about functions with limits. We talk about differentiable functions. We talk about Riemann integrable functions. The whole idea of mathematics is centered around the object called the function. So without it, we'd have a hard time communicating with each other. So now, like I said before, the notation here is fine, but normally we want to think of the function notation, and we would say something like this: f of 1 equals 2. That is input 1, output 2. And if you have a formula, you can evaluate the function. Here, we know what the outputs are because they're given to us. F of -3 equals 5. F of the square root of 2 equals 0. And f of 6 equals 2. So this is what we call the function notation. Now, normally, we'll just say, in our course, our focus will be real valued functions. That is, we're going to have functions that have real output and real input of a real variable. So the focus will be real input, and even though we could have complex imaginary input and imaginary output, real input, real output. Because when you study the calculus, the focus will be the real value of a real variable. So in our course, sorry, I say the word and I leave it out, how sad. In our course, our focus will be real valued functions, use your little caret, real valued functions of a real variable. I always say so much and get ahead of what I'm writing. So in our course, our focus will be real valued functions of a real variable. Okay, so good for you. Or good for me that I've corrected that. So again, what does that mean for us? Well, we've actually been doing this already. So when we look at our college algebra experience, we already know that we've studied all kinds of interesting functions. Rational functions, so here's an example. F of x equals 4 minus x divided by 4 plus x. So the first part of the functions was basically just a brief introduction to the terminology. And so now we can now look at functions that are actually defined by formulas. So we'll say f is defined by a formula. Now, when it comes to functions of a real valued functions of a real variable, the computation of the domain is usually reasonable. Okay, in most cases in this class, if I ask you to compute a domain, you will be able to compute it. The range may or may not be simple. The range may require techniques of calculus. That is, you may not be able to say, well, the actual set of outputs is this. You may have to use some optimization techniques in calculus. So if I ask you for a range, it'll be something that you will be familiar with, and the technique will be available to you to actually compute it. Now, when we look at this, let's just practice a little bit. First, before we do anything, let's just go ahead and look at the domain. Because, for instance, if you were tutoring someone and they said, well, let's evaluate this function at some elements. And then the first thing you would say is, let's determine what the domain is. So we could say domain of f. We'll do this formally, and then we'll write it in a way that maybe WebAssign would ask us to do. We would say, here's the formal definition. X real, and you don't always have to say X element of R. You can just say X because it's assumed to be in the real numbers. But I'll go ahead and do it formally, at least for now, such that 4 plus X does not equal 0. Because when we look at this formula, if we're dealing with polynomials, we don't have to worry about division by 0. But this formula basically says you input an x, take its negative, add 4 in the numerator, and downstairs you input the x and you add 4, and you take the division or the ratio of those two numbers. Now, the idea is in mathematics, the process of division by 0 is not something we understand. That is, it's not defined. And so the beauty of division by 0 being undefined is that it gives us all kinds of nice objects called asymptotes, which again are something that we learned about earlier in college algebra. But now when we look at this, we're thinking, okay, now I'll shorthand it a little bit. This will be all x such that what? X does not equal -4. So now we're just a little bit freer here. We don't write all the notation down. And then we're thinking, okay, because if I want x plus 4 to be non-zero, I basically just solve this, and that just excludes -4. So anything that would be down here in the denominator, you would say, okay, I must exclude zeros. Maybe it doesn't have any zeros. So then there would be no exclusion with studying the denominator. And then you say, okay, well, maybe WebAssign would ask me to write this in interval notation. So I would say -infinity to -4. And then the connection, don't put an ampersand, use the union symbol. And of course, the WebAssign has the little palette where you go and borrow the mathematical notation. So you know how that opens up, and you click on what you need. So get some practice with that. When you want to connect intervals, this or that, you use the union symbol. Now you're thinking, that sure is a whole lot of work to write that. Isn't that easier? Well, sure, but many times in the WebAssign, they will say write using interval notation. Now, what's good about this is that you look at this and say, that's all real numbers except -4, which you can easily see here. But the interval notation, as you well know, is very popular. It's utilized often. It's become convention. So I want you to be able to do that. So now, just remember, it's fine for an output to be 0. It's fine as far as that goes. It's fine to be able to put in 0. The thing is, when we compute the domain, we are looking for the largest set of real numbers for which the output is real. So you would not say the domain is -4. You compute this and say, oh, the domain's -4. What you mean is that -4 is not in the domain. So when we do the real valued function of a real variable, we're looking for the largest set of real numbers for which this provides, for which the output is real. So this is the largest set of real numbers for which the output is real. Now, again, it will not be the case in many instances where we will want to do the actual range. But in cases where it's computable, I will ask you that. But the domain is pretty much a given. You will always need to know the domain. When you do calculus problems, the first thing you do is, you're doing graphing or you're doing an optimization problem. You're like, okay, find the critical numbers. Well, first know what the domain is, because the critical number must be in the domain. And you can't work with them unless you know what the domain is. So always do the domain calculation. Now, when we look at this, your background from college algebra would also say that x equal -4 is actually a vertical asymptote. And then you're going to say, doing the comparison of the coefficients of x, you would say it has a horizontal asymptote of y equal -1. Now, we will review some of that, but when you think about the range, this is a very simple problem to do range-wise. Now, what you can see here when we think about horizontal asymptote in this particular case, you can see that that would be a -1. That is, y equal -1 would be a horizontal asymptote ratio of leading coefficients where the degree here and the degree here are the same. And so you would think probably can get any output except -1. So here's a little trick to figure that out. We're going to say, let me just show you this. Say, let C be a real number. Again, I'm utilizing the fact that you graphed rational functions before to appeal to what you know about asymptotes. So let C be a real number. Then suppose that we assign C to be the output. I just want to give you a little exercise here that can help you out. That is, suppose that C is the output. let's figure out which C can actually be an output. And we can do that for this equation, for this function. So now we're going to cross multiply. So just put the 1 here. So this is going to be C times 4 plus X equals 4 minus X. And so what we want to do is solve for C like we're doing like an inverse computation. So we have, in this case, 4C. We'll actually solve for, in this case, see what C is. And I didn't multiply everything out, which is good. So now C minus X, 4 plus X. Now, let me say what I did here, and let me just say why I did this and going backwards and forwards. This is what I started out with. So let me get my logic to the point that's going to make sense for you here. Notice if we look at this and say, okay, what are the possible inputs here? Let's solve for X. So let me write it this way, not just go in a circle. Solve for X, like we're doing an inverse. So yeah, this is true, but that's the same thing we started with. That's what math does. You go backwards to go forwards. So here's solve for X. So now when we cross multiply, we have C times 4 plus X equals 4 minus X. Now multiply everything out. 4C plus XC, how interesting, equals 4 minus X. Now, again, we want to solve for X, so let's put all of our X's on one side. So we have XC plus X equals 4 minus 4C. So again, add X to both sides, subtract 4C from both sides. We have all our X's together. So we have X, factor the X, C plus 1. And here we can factor a 4 if you like. We have 4 times 1 minus C. And so now X equals 4 times 1 minus C times C plus 1. Okay, so this is the computation I was talking about. Now, I'm not saying this is easy, but I know in your previous classes, you just kind of use your fancy calculator and you say, oh, okay, well, -1 is not in the range. Well, that's not a proof. That is not a proof. And I don't want you to depend on calculators because they don't make you any better at math. They actually make you worse. We need a calculator when we need to get a nice approximation because we need to move the problem forward to look at magnitudes. But here, notice, if we're saying that C is an output, if we look at this equation right here, we see that C cannot be -1 because then this is undefined. So this implies that we must kick out -1. And that's exactly what I said here. That is, when you look at the ratio of leading coefficients, we get a -1. So this implies, now of course, what I've done here, ladies and gentlemen, is dependent on the fact that we can do this. And if we can't, that's okay. We might have to use other techniques. But this basically says that the range, and we'll just say range of F, we don't have a abbreviation for that. We would say all Y, we'll just give it a name for the outputs Y, element of R, such that Y does not equal -1. So we'll think of X as the inputs and Y as the outputs, or we can say -infinity to -1 union -1 to infinity. Now, like I said before, if I ask you to do a range calculation, okay, unless it's just a simple definition like a polynomial or a square root function where by definition you can intuit it that way, that's fine. Or it's something that you can understand. There will be a technique that you can use. So if I gave you a problem like this on a test, and I'll say, determine the range using an equation, or I'll just say, provide the algebra to determine the domain in the range, you would be able to do this. So let's just kind of review what I've done here. Don't go forwards to go backwards, clearly. So what you do when you're trying to determine a range where this technique works, you use any letter you like. I just used a C. You could use theta. I don't care. That letter doesn't matter. Just don't use an X. So you set, in this case, the function formula equal to C. And the key is to solve for X, like you're doing an inverse function computation. This is good practice for that. This is actually good practice. We did an inverse calculation. Now, so again, solve for X. So you will be able to solve for X. And then you look at your expression for X. And you say, okay, all values of C are fine here, but if I look at the denominator, I see that C equal to -1 causes division by 0. And then that's not a real number. And so you say, this implies that C does not equal -1, but any other real number would be fine. Any other real number here would be allowed. So now you can go over here and say the range is all Y such that Y does not equal -1. So I want you to be aware that there are certain instances where you can actually compute the range algebraically, just like we think about computing the domain algebraically. Okay, I don't want you to think, I mean, and think about it, ladies and gentlemen, if we are completely dependent on a computer algebra device to do math, then who's learning? No one. Okay, so utilize the technology when we need an approximation. When you get to your engineering courses, you may do some computer programs. There may be cases where using the technology is the desired effect. That is, you work the logic to write a computer program. When we do mathematics, it's like we're writing a program, and we have to check each step. I mean, this is true, but we already knew that. So we're thinking, wait a minute, what do we need to do? Oh, we need to solve for X, and then we can use this formula to figure out what the range is. Now, let's just do something really simple. So, for instance, now, you know, you can put any C over here and figure out what the domain element needs to be. So let's just say here, let's just do a little practice here. Say that C equals 2. Okay, say, and that's in the range. So we'll say let 2 be in the range of F. Let's figure out what the input is. And of course, this is only working because this is, in this case, is a one-to-one function. So let's just see. So that means this implies, using our formula here, that X equals 4 times 1 minus 2 divided by 2 plus 1. So this is 4 times the -1, 4 times -1 divided by 3, or -4/3. So now we see that F of negative, this is the backwards problem, equals 2. You see that? So you know how to substitute numbers into a function. Now I'm showing you, once you do this, you can figure out the input that gives the range. Okay, so the beauty of this problem here, when you do this calculation, you can be like predicting. You can predict here. Now you can say, okay, if I've got this formula, then you give me some element in the range and I'll tell you the input that maps into it. Okay, so I want you to be familiar that you don't have to look at a formula and just give up and say, I can't do this. The algebra will guide you to the solution. Okay, now in your WebAssign, they'll have you substitute different expressions for X. So let's just practice one of those just to give you some practice with that. Let's do some algebra. So in the WebAssign, they asked you to do the following. That is, we have this function here. Let's just remind ourselves what f is. We've beaten it to a pulp, right? And when you do these problems, enjoy them. How do you get good at math? How do you get good at anything? You do it. So for instance, let's just say compute f of, in this case, what did WebAssign ask me to do? X squared minus 4. Now, this is a common procedure in mathematics, engineering, physics, whatever. Now what we want to do is replace, this is going to help us with compositions, replace x with x squared minus 4. So remember, we like this function notation because this says replace x with x squared minus 4. So there's no reason that we shouldn't review this right now and get good at it. So by the time we get to inverses and the compositions, we'll already know how to do it. So now we say, okay, 4 minus x squared minus 4. Remember distribution. Distribution, like I said before, you be sure to distribute. So you use your parentheses. I don't want to see errors like this. That's not what a pre-calculus student does. Be careful with what you do. Do like Professor Ron. Well, that's true, but it's not helping me. Let the algebra and let the math tell you what to do. 4 plus, and now if you like, we've got a plus here, but I'll just say x squared minus 4 just to keep it consistent. Now, the distributive law says I need to distribute the negative. So I have 4 minus x squared, and then minus minus is a 4. Downstairs, I'm just distributing the plus sign. That's easy. So I have what? 4 plus the negative 4. I'll just write 0 plus x squared. And so now, 4 plus 4, I get 8 minus x squared divided by x squared. So that's just a little algebraic computation. It's not difficult to substitute numbers into a formula, but sometimes you will substitute other expressions. So again, whatever is in parentheses is where you go into the formula and replace the independent variable with this new expression, just like you did in college algebra. Now, I've got some examples here that I want to look at. We want to do a difference quotient, but I want to do one more example with the range and domain. I'm a big fan of understanding domain and understanding range when you can, because that means you understand what the symbols are telling you. So here we have a very simple, and of course I want you to remember all of the simple functions from college algebra, the x squared, the square root, the cube root, the cubic function, absolute value, things like that. We'll manipulate those with the transformation. So that'll be a blast from the past. So say we have this particular function, t plus 1 square root. So again, just remember, I'm not going to ask you to manipulate problems with range unless you can do what I did on the last problem, be able to actually do the computation. So just keep that in mind. I'm not going to push you off into the deep end. Now, notice here, this is going to help us with transformations. The principal square root is a non-negative function. So when I have f of t equals the principal square root of something, okay, this by definition is greater than or equal to 0. Okay, we know that by definition. By definition. So when I think about the range, clearly as t gets larger, the output gets larger. So the range here is easy to compute. We don't have to do anything extravagant like we did on the last problem. The range of f will be bracket 0 to infinity. This can get as large as you like. It's just that it can never be negative. the principal square root is non-negative. Now, you can do some other calculations here with algebra and things, but they're not going to give you the kind of detail that you would get with the last problem. So again, we can use the fact that when we define the principal square root, it is non-negative. Now, let's also think about this. Before we talk a little bit about some transformations, we've got the range. Let's think about the domain. So this is the other problem, and then there's an interesting little domain problem for Cleversine. So we'll have all t real such that, now of course this is a principal square root and we want the output to be real. So that means that the argument here is either called the argument or the radicand. Argument is fine because we're going to use that in trigonometry. What is the argument of the radical of the square root? What is the object of which we are taking the square root? And so we say t plus 1 must be greater than or equal to 0. So that just means that if I take the square root of a real expression, then that expression must be non-negative. I can't take the square root of a negative number and the output be real. It will actually be imaginary. So again, real valued function of a real variable. So this will mean all t such that t is greater than or equal to -1. Now, when you think about this and you look with this, you have a function that's never negative, that's 0 or positive, and then the inputs must be -1 or greater. Now when we think about this, we're thinking, okay, well, we know what the square root function looks like. Let's just go ahead and draw it. This is from our college algebra days and even your algebra 2 days. That is, we had put in a 1 and then a 4. You get out a 2. So it has that shape, vertical tangent here. It goes out like this, and it just keeps going. Always increasing, but as I like to tell my students, it takes its time. Now, for this is just, we can just call this y equal the square root of t. Now, if we think about this function, what's happened here? Well, we've replaced t with t plus 1. And we know that that is, and we'll talk about this next class, that is a left shift by 1. So now we notice if we do something like this, t, we'll say left shift by 1. We replace t with t plus 1. And that's the anomaly of doing horizontal shifts with algebra. It goes to the contrary of the vertical shifts. The vertical shifts are very intuitive, but you have to think about what's going on horizontally here to be able to understand this. And this is something you did in college algebra. So now when we draw this function, I'll use the black, we just shift everything over 1. Here. So this is y equal the square root of t plus 1. And so now we see that the domain is indeed -1 to infinity. The idea here is that this tells us what the domain is algebraically by definition of the principal square root. And then when we analyze function transformations, we get the same thing. That is, now when you think about it, these points 0, 0, 1, 1, and 4, 2 are moved. They're horizontally translated. So this means left shift. So we subtract 1 from all the x coordinates. 0, 1, 3, 2. So we'll say more about this when we review this, but this is one of the major transformations that you use in mathematics from college algebra and forever. When we do trigonometry, we will use of trigonometric functions. So the idea is now that you look at the square root function and you think about this and say, oh, okay, by definition, non-negative. And then I want to make sure that my output is real. So how do we figure out the domains of real valued functions of a real variable? Well, we basically do two things. We check for division by 0, and we check that if we have an even nth root, that the argument is non-negative. Now, that's not difficult, but it does help us to understand why when we take calculus, that these types of computations are very important. Because if we're looking for a set of differentiability, that is, where does a function have a derivative? We first have to start with the domain. We have to start with the inputs, because anything outside of the domain is not going to matter to the function if we're considering real value functions of a real variable. So the domain computation is something that we really do need to master. And what you can see here with these types of computations, that everything we do is connected. That is, when you come up with some new mathematics, ladies and gentlemen, you're going to have to make sure that it's consistent with what's already out there, because I think we've had enough smart people decide that what math is actually out now is good. It's been tested many times. Now, what I want to do here is to look at another domain computation. We have g of x, and then of course the WebAssign will give you lots of practice with substituting into functions. You'll find that to be just good practice, but very simple. So we have the square root of x divided by 7x squared plus 6x. You're thinking, with all those horrible inequalities we had at the first part of the lecture, this is easy. So this is what I want to impress upon you. You don't always have to use the symbolic computation that we did with the word problems and the inequalities here. This is just basic analysis using definitions. Now, for instance, when we look at this particular function here, we have in the numerator the square root of x, and in the denominator, we have a quadratic function. Now, let's just try to look for the two items I talked about before. We don't want to take square roots of negative numbers, and we certainly don't want to divide by 0. So let's check the denominator. Let's try AC. We get 7 times the negative 1. Now we're thinking, wow, jackpot, jackpot. Why? Because the sum, the z and the w, are actually 6. So we can go ahead and use Professor Ron's AC lemma. So we have 7x squared plus 7x minus x minus 1. So the techniques we reviewed are now important doing functional analysis. Now, of course, we factor a 7x, and we get x plus 1. And here we factor a negative 1 and get x plus 1. So now we see that we've rewritten the function to showcase what's going on in the denominator. So now we have what? 7x minus 1 times x plus 1. Now, here's a little trick that I want to share with you that we're going to do when we review solving equations and equation theory with polynomials. I'm going to go ahead and factor the 7 from this factor here, just to rewrite it, just so we can see some algebra at work. Now, of course, these are a product of two factors. So here I'm going to factor the 7, just like we did the very first week. So I get an x, and then I have to pay for it, right? If I factor the 7 from both of these terms, then I have to divide this by 7. So when I multiply through by the distributive law, I get the -1. And then, of course, the x plus 1 is fine. So now when you look at this, this gives you more detail about the function. There is nothing wrong with this. This is very clean and concise, and it makes for good show in a textbook. But the first question might be, what is the domain of this function? Now we look over here and say, well, what does the square root say? We'll say number 1, square root x implies that x must be non-negative. That's just by definition. That is, when we take square roots of real numbers and we want the output to be real, the argument must be non-negative. So again, very straightforward, but very important. And now when we look downstairs, we don't want to divide by 0. So I've written this so it's real easy to figure out what the zeros are, just like we're doing the fundamental theorem of algebra with the theory of equations like you did in college algebra. And so here we see that 1/7 won't work because that'll make it 0. So we'll say x does not equal 1/7. And now when we look at this factor, we don't want to divide by 0, so we don't want x to be -1. Now when we put all of this together, what does it imply? Well, -1 is just kind of isolated, and it's really out of the action altogether because it's less than 0. So we don't even have to worry about that. The only thing that's going to impact the domain, because we know this is required from the radical, is this 1/7. So any non-negative real number that's not 1/7 will work. So this implies that the domain of G now equals, well, let's start with 0. And we move up to 1/7 and use our parenthesis. Remember in mathematics, and this is conventional, this is standard. When we want to include an endpoint, again, we use a bracket, but we want all real numbers increasing to a particular number. Anything less than 1/7 but greater than 0, we use here a parenthesis. So this excludes 1/7. But any number less than 1/7 and greater than or equal to 0 would be included. Union, and now we're thinking we still need all other positive numbers, so we have to repeat this again, 1/7 out to infinity. Now, here's one thing that I find that students often have an issue with. Ladies and gentlemen, infinity is not a number. It is simply a behavior, so to speak. We think of infinity as just being out into the stratosphere that exceeds any number we can come up with. And so we can't bracket it. All we can do is use a parenthesis. So this means that you can take any number that you can think of as positive. You know, if you give me 1,000,000, I'll give you 1,000,001. Okay. If you give me 10 billion, well, I'll multiply it by 2. So this simply implies that you can take any positive number. We just have to exclude what? 1/7. And we're also allowed to use the number 0, which has that kind of dual status. It's neither positive nor negative, but we can make it that way if the problem needs it. So when it comes to working a domain problem, if we have radicals, we must make sure that the argument is non-negative. If we have variable denominators, we have to ensure that we do not divide by 0. But again, the thing is, students feel like, well, the -1 got left out. Well, it did, but as far as this function is concerned, it has no impact. The -1 would never make any sense, and it's isolated. So when you all take topology, in advanced calculus, some of you will end up in those classes at the university. You'll spend more time with isolated discontinuities and things. But this is even more pathological because it's not even in the domain set. But when we talk about isolated discontinuities in a topological sense, this will make a lot more sense. Now, let's look at another example. What I have here that I want to do is to just end with a computation of the difference quotient. Now, when you look at this particular problem here, this provides a good analysis of all the things we've been reviewing. Now, when you take calculus in the Larson text, if you take my class, I use the WebAssign in the Larson text, we might be interested in a difference quotient. And what I did, I went to the WebAssign and I just picked some examples here. And here was one example. We have f of x, just to get some practice with functional algebra. Now, this would be a fairly simple problem to figure out range. And now, of course, here you're thinking, well, this can be 0, this can be 0, and because of that vertical asymptote, it can explode to any real number. But I'll give you a little break on that. Notice here, this is just like the function we worked with initially. And we can see now, using what we've already proven, that the range will not include 1 and the domain will not include -9. So we can go ahead and write that because we've become professional at that. The domain will be -infinity to -9, union -9 to infinity, just using the technique that we worked on previously. And then, of course, the range will exclude the ratio of leading coefficients, which is 1. Now, when you look at this, here's what WebAssign asks you to do. They're going to say, write f, and the notation will change. Sometimes it'll be x plus delta x, it'll be x plus h. In this case, they want you to do a plus h. I just want you to be comfortable with whatever is here and just use it. Basically, the difference quotient will be part of the definition of the derivative when you take calculus. This is one of them. There are other forms of the derivative, which Professor Ron actually likes better, but we'll cover that when we get to it. So we're going to look at a difference quotient where, of course, we're not dividing by 0. And what we're going to do is we're going to use this function. So we're going to replace x with a plus h. We're going to replace x with a and take the difference and then divide everything by h. So let's go ahead and do that. First, we're going to bring the 1 over h outside. We're just going to say 1 over h and pull it to the side, just like saying if we have 2/3, this is like 1/3 times 2. That's what I'm doing here, just to move the h over because it's in the way and all the action is happening upstairs. So I'm just going to do this little trick here to remove the h to the side. But we don't want to forget it. That's the thing. We factor something and then we leave it and then we wonder why the problem is wrong. So now we're going to do f of a plus h. So a plus h. And then x, we have a plus h plus a 9. So here we replace x with a plus h divided by a plus h plus 9. And now we do f of a. Well, that's easy. We just replace x with a, so we get a plus h, 9. So now, moving this 1 over h outside is a big favor to our calculation. We can do our common denominator here and keep this out of the way. Otherwise, it just gets in the way.
So now notice, I'll use the other color here. We have this distinct factor downstairs, and we have this one. They are not multiples of each other. So we need the product of this and this as the least common denominator. So let's do a fraction bar. So we have A plus H plus 9, and we have A plus 9. Now be sure to write the 9 so they don't look like A's. You know, that's the thing. Don't put a tail on the A that makes it look like a 9. And then, of course, we need to pay for things. So now notice, when we look at this, we have an A plus 9 here that we don't have here. So we've got to multiply the A plus H times the A plus 9. And then here, we have the A plus 9, but we don't have the A plus H plus 9. So we have minus A times A plus H plus 9. So again, we're just getting a common denominator. Now what we want to do is multiply and collect terms. So go ahead and write your denominator, A plus H plus 9 times A plus 9. And let's multiply everything out. So we have an A times A, so we get an A squared. A times 9, so we'll just write it with the 9 first, 9A. And now H times A, or plus HA, and then H times 9, we'll just write it as 9H. And let me give a little bit more room here before I put in my brackets so I don't have to smash everything in there. So just go ahead and bring this over a little bit more. And now we're going to multiply all of these terms by negative A. So we get negative A times A, or negative A squared, and negative A times H, or we can do the H first, and then a negative 9 times an A. Now we see that most of the terms absorb. That is, these absorb, this absorbs with this, and then this absorbs with this. So everything pretty much goes away. So now we have 1 over H, just using basic algebra, and the only surviving term, let me just put a box around that. This is the only term that survives, the 9H. So we have 9H, and then we have A plus H plus 9 times, and sorry I didn't close my parentheses there. Professor Ron had to close parentheses. Now, the idea here is though none of this algebra is difficult in the sense that it's just basic distributive law, getting a common denominator. But now we can see that the H's will absorb. That is, this 1 over H has been hanging out to the left while we did all of this work, and now we can see that these two factors will absorb. So just put a box around them. You know, I don't tolerate the slash lines, never use that. You can put underline things or whatever, that's fine, but do not use slash lines. That is poor notation, and I don't want you to keep doing that. So now we're just left with a 9, and we have an A plus H plus 9, and we have an A plus 9. Now, one thing that you might notice about this, that you're thinking, okay, what is the reason for doing this? Why would we even care about this? Well, when the derivative, the rates of change were defined, we basically look at the slope of a secant line. And so what we're interested in is allowing the difference between the 2 points to basically converge to 0. So this H is like that factor that separates 2 points on the graph of a function. And we allow the H to go to 0. Now, the definition says if the limit as h approaches 0 or whatever variable you're using actually exists, then you have a tangent at that point, a tangent line. And so now when you take your calculus, if you look at this, the h can basically converge to 0 or approach 0. And then what's left here? You just get an a plus 9 times an a plus 9. So this will later imply in a calculus class, we'll use the notation of f prime of a. This is what you're going to do when you take my Cal 1 class. This will be f prime of a is 9. And now we'll have two copies of this because the h basically disappears in the limit. So we'll say a plus 9 quantity squared. That is, in this case, h approaches 0. So we replace h with 0. So this is why you do this. This is not because we just want you to do extra work. Now, there are other forms of the derivative that we will discuss when we take Calculus 1. But what I want you to do with these kinds of problems is just practice the algebra, okay? Practice computing domains. And our favorite problem, which I put over here, let's see, what did I do with it? Oh, practice the trick of figuring out the range with this technique. All of these problems utilize basic algebraic techniques. When we started out the class, just as a review here, when we started out the class, we were doing symbolic calculation. That is, we utilized multiplication without even actually doing multiplication until we had to, and it was really easy. So we go from symbolic computation to another form of symbolic computation. So what we're seeing here is that the types of computation we do with letters, we do with numbers. So there is no difference. So what I want you to do for this week is practice the word problems with the symbolic computation. We have office hours today in the afternoon. Practice utilizing your good algebraic techniques to determine domains, and in the cases where it's possible, determine a range. Now, the WebAssign won't say a whole lot about range, but if you see an example that's similar to one we've done, then make an effort to actually compute that. Just know that there will be some other ideas that you learn in later courses that will allow you to compute extreme values that we don't have at our disposal right now. So just remember, as we move into the next lecture, we're going to talk about transformations, again, review from college algebra. So go ahead if you like. I'll go ahead and in the next day or so, go ahead and put up those new sections. So if you get finished with this, you can go ahead and look into that. And just remember that as we start the new week, we have our homework due for the previous week and then our quiz on the next day. And this will give you time to actually do your work and have time to think about it and then process and hopefully keep you on the schedule. Just remember, the pre-calculus class is like Calculus 1. It never stops. And when it's over, it's over. But I want you to have a good experience because you spent consistent time on the class. So thank you for your attendance today. Everybody have a great day. Get some rest if you need it. Get some exercise if you need it. And we will see you next week. And hopefully I'll see you in some office hours. And I think the Student Success Center is going to have a possible Zoom problem session on Saturday that they will make available to you all. And I will put that in an announcement that you can actually take advantage of that. It'll be like on a Saturday. And what they're trying to do is utilize some of the wonderful tutors that we have at the San Jac North Success Center. and they will share their expertise with you. And one of the tutors said, well, what would you like them to do? I said, well, help them with their WebAssign, help them with anything. So I will post some information about that. But everybody have a great day and take care.
Have a great day, sir.
Bye.
Have a great day, sir.
You too.
Thank you.
Thanks to everybody. I really appreciate this. I know it's hard taking math this early in the morning.